That's nice. Good evening. We don't normally get that. Good evening. Welcome to the 2025 John Hines Memorial Lecture. As you may know, John was a very generous benefactor of this institution. And since 2013, his family have sponsored an annual lecture in his memory. And we're pleased tonight to welcome several members of his family for the lecture. Our speaker tonight is Professor of Astrophysics at Oxford University. He's also Professor of Astronomy at Gresham College in London and a Research Fellow at New College, Oxford, as well as various other things, including lead editor for the American Astronomical Society. He's also, as some of you may know, for 25 years been a presenter of the BBC's Sky at Night. At first alongside Patrick Moore, who described him as eminently suitable for the role of TV presenter, and I'm sure those of you who watch the programme would agree. He describes himself as a distractible astronomer, specialising in galaxy formation, machine learning and occasional planet hunting. Away from work, he says he cooks, suffers through being a fan of both Torquay United Football Club and Somerset Cricket Club, and spends as much time as he can with a rescued lurcher, Mr. Max. Please welcome Professor Chris Lintott.
Thank you very much. Thank you for coming out on what's beginning to feel like quite an autumnal and wintry evening out there. It's a delight to be here. This is a magnificent place, and it's just such an honour to visit and to learn a bit about the institution and about the contribution of John to it as well. So thank you very much for having me. Really what I want to talk about this evening is how astronomy gets done, how we come to understand the cosmos, because I think it's very easy to give the wrong impression from a grand stage such as this. It's very easy to do the thing that perhaps you've heard astronomy lecturers from here do before, where you say something about how the universe has a few 100 billion stars in each galaxy, and there are 100 billion galaxies scattered throughout the universe, and we all think about the vastness a bit. And I just think it's very easy to give the impression that in such circumstances, I have some deep understanding of what it means to live in a universe with 100 billion galaxies, each consisting of 100 billion stars, and I don't. I've just got used to saying the word billion a lot more than most people. And actually, the fun thing about astronomy is that you can get quite profound and interesting truths out of quite simple and surprising experiments. So tonight's lecture and the book on which it's based are really an attempt to talk about those things, those slightly hidden stories. For me, all of this is rooted in the fact that I'm an observational astronomer. I like looking at the universe. So we can do a bit of that, thank you. So this is a terrible picture of the night sky. This is twilight. There's a horizon. It's dark. You can sort of see the glow of the remnant sunlight at the bottom. And hopefully you can just see just above my head here, there's an evening star in this sky. So far, so simple. But if I zoom in on that star, we see that it's actually a double star. There are two there. And the reason that there are two things there is that this is not a picture taken on Earth. This is an image of the night sky from Mars, taken by one of the Mars rovers, and the twin evening star is, of course, the Earth and the Moon. And so we get a view of ourselves from another planet. It's a triumph, I think, of this kind of observational astronomy. And again, you can slip into Sagan mode at this point and start talking about how everyone who's ever lived has spent their lives on this pale blue dot and so on, but I won't do that. For me, this journey really started as a kid. I was a kid fascinated with the stars. My school had an observatory that they let me use, which still astounds me slightly. And mostly what I did was I used a small telescope that I'd bought, funded by selling ice creams on Torquay seafront for a couple of summers, badly, to look at this object. This is the Orion Nebula. It's our nearest star-forming region. It's a place, a nursery, where the gas and dust that you see in this wonderful Hubble Space Telescope picture are collapsing and forming stars, the light of which, buried deep in the heart of the nebula, is lighting up their surroundings. The great astronomer William Herschel, the discoverer of Uranus, the great English observer, described this object as an unformed fiery mist containing the chaotic material of future suns, which is lovely and makes me wish we still wrote scientific papers like that. But what I like about this object, it's obvious in the night sky. If you know Orion in the winter months, it's in the sword that hangs down from his belt. One of the stars, even with the naked eye, appears as a fuzzy patch, which is this nebula. But even in a small telescope, it sort of looks like this picture. Not in detail, but you can see on clear nights, if you're patient, you can see a three-dimensional shape to this nebula as the gas wraps around the stars. And as you look longer, you begin to see some of the colours, the green glow of oxygen in particular. And it's easy to connect what you're seeing through a relatively modest instrument to the glorious professional photograph. So I've spent many evenings in my life looking at this object, but on one of them, when I was about 14, I nudged my telescope. It's a simple thing, no computer drive or anything. And it moved north and it showed me this. And this is a cluster of stars. The nebula is now off to the bottom of this picture. This cluster of stars fit perfectly in my field of view. I'd never heard of a cluster of stars north of the Orion Nebula. And this is going to be difficult for younger members of the audience, but you have to realize I didn't have the internet at home at the time. But I did have a book, which is like the internet, but printed out. I had an atlas, and so I got out Sky Atlas 2000. I looked up this position, and there's no cluster marked. And I remember thinking that maybe I'd made a discovery just by looking at the universe. And I got a pencil. Can't have been that confident because it was a pencil. I put a cross, and I called this Lintott 1. And when I got to school the next day, I discovered it's actually called NGC 1981, which is not as good a name, but it was discovered in the 18th century. It's a well-known cluster. It's a target for astrophotographers and so on. But for a long while, I thought of this evening as the point where I learned a lesson about how astronomy was done. I thought that I'd learned that you couldn't make a discovery by looking at a single object, that you couldn't do it with modest equipment. As I grew up, went to university, went to do my PhD down the road at University College London. I learned, I thought, that modern astronomy was done with big facilities like this. This is the Sloan Digital Sky Survey. This is a telescope. The mirror in the heart of this thing is about 2.5 meters across. It's on a hilltop in New Mexico, where they have about 320 clear nights a year, so it's about the same as Highgate, I'm told. And Sloan did this extraordinary thing. For 8 years, this telescope on most nights just let the sky turn above it. And as objects drifted through its cameras, it took color pictures of what amounted to eventually several billion objects. And on the clearest nights, about 1 million of those objects were faint fuzzy patches that seemed to be distant galaxies. So like the Milky Way, systems of a few 100 billion stars, relatively isolated in space. And on the clearest nights, Sloan went back to these galaxies and it measured the distance to them. So we got not a two-dimensional map of the sky, but a three-dimensional map of our local universe. And here is that map. We're flying through it. We started on the Milky Way. And as you zoom outwards, you can start to see that there's structure in space. So the big discovery of this survey was that space is lumpy, that there are places where there are lots of galaxies and places where there are very few galaxies. And it is astounding, even in pseudo-Sagan mode, to say, each of these is a galaxy with a rich history like the Milky Way that we could spend a lifetime studying, and yet in this data set we have about 1 million of them. This is a very rich set of scientific data, 8 years worth of data and images. And mostly, what I thought the point of this was that astronomers would take all of this, boil it down, and write papers like this one. This is The completed SDSS-4 extended baryon oscillation spectroscopic survey, measurement of the area and growth rate of structure of the emission line galaxy sample from the anisotropic power spectrum between redshift 0.6 and 1.1. I know you're familiar with it. Here's the exciting graph from the middle of it. And this is genuinely really exciting science. This is a measurement of how much the universe has expanded in the last 10 billion years. And it uses all of those individual galaxies as trace particles within our universe. And this is the kind of science that we're used to hearing about and thinking about. But I also think it's important that we notice that one of those million galaxies looks like a penguin. Because when you look at the penguin, you can ask scientific questions about it, like, why does it look like a penguin? You can ask why it has this dust lane. You can ask why the blue bits, which in this color scheme are newly formed stars, they're brightly shining massive stars that are formed in the last 10 million years, why they seem to stick around the edges of the galaxy. You can ask why there's an egg down here and whether this has anything to do with it. All of these questions are just as valid and tell us stuff about the universe in the same way that boiling all of this data down to make a graph does. And you could do a whole PhD on the Penguin Galaxy. In fact, somebody is doing so because we just got, with our new telescope, JWST, which looks in the infrared, we just got an infrared image of the penguin. And now we have some answers. So the egg down here is connected. There's a bridge of light that runs between this thing and the other galaxy. Possibly this galaxy has passed through and disrupted the gas. But we have new questions like, what are these feathery things down here? Why do we have clusters of what must be star formation, but only on one side of the galaxy? What's the bright source in the middle? All of these are important questions, and we sometimes learn about the universe by accidentally spotting a penguin, just as we do as carrying out the precise physics experiment that we thought we were building a telescope to do. So it's that kind of story that interests me, and that kind of work that I want to do. Let me give you another example. Let's come a bit closer to home. Let's come back to our solar system and talk for a bit about Saturn. Saturn is, of course, the best planet. I think the other acceptable answer to that, to be fair, is Earth. But those are the two right answers. Saturn has many things going for it. Just the planet itself is astounding. It has the fastest winds in the solar system, a complex layered structure that means we don't know what day, the length of the day is on Saturn. It has at the North Pole, which you can see at the top here, you can just about see a purplish hexagon, which if you read the wrong parts of the internet is clearly built by aliens, but is actually created by the interaction of long-lived cyclones, storms, at the pole. So the planet is fascinating. It, of course, has its rings, which some people think are short-lived, perhaps the result of a recent, last few 100 million years or so, a recent collision between two moons, or maybe they're long-lived. Maybe they're a relic from a time when the planets were forming. And the astounding thing about the rings, which have this complex structure that's imposed on them by the gravitational pull of Saturn's 140 or so moons, is that even though we can see them from Earth with binoculars or with a small telescope, normally you can't, at the minute they're edge on to us, so it's quite difficult at the minute, but normally you can see them with very modest optical aid. The whole structure is only about 20 meters thick. So this is a very thin thing, and understanding how that can persist and why it's there is interesting. And then Saturn also has, I think, the most intriguing moon in the solar system, a place called Titan, which it's the only moon with an atmosphere. It has a thick nitrogen atmosphere like the Earth, but instead of water in its atmosphere, it has complex hydrocarbons. It has methane and ethane, and it rains those chemicals. So methane and ethane falls on Titan in raindrops the size of lawn tennis balls that fall slowly enough in its puny gravity that you could dodge them if you were standing on the surface. Titan may be a place where the beginnings of life have happened. It's an edge case, a place that's nearly but not quite habitable. It has lakes and oceans that come and go with the seasons. And so for all of these reasons, Saturn was the target for a probe called Cassini, which was the most expensive and long-lived probe ever sent to the outer solar system. It spent 17 years exploring the Saturn system and addressing many of the questions that I've just outlined. But at no point during its construction or planning or travel to the ring planet, or indeed when it got there, did anyone really give any thought to the fact that on one of its first orbits around the planet, Cassini went past a tiny moon called Enceladus. This is the best picture we had of Enceladus before the Cassini mission. This is from Voyager in the late 1970s. It's got a surface that's mostly water ice. These black dots, by the way, are artifacts of the pictures. But it's a surface of water ice. It gained brief notoriety in the early 80s when people realized it was the most reflective thing in the solar system, but no one really came up with a convincing explanation why, other than that water ice is quite shiny. And it's about the size of the British Isles, so it's relatively small. But Cassini happened to fly past it, and so uninterested were the scientists, who were mostly planning for their first visit to Titan, that not one of the spacecraft's cameras were turned on for that first encounter. In fact, all but one of its instruments were switched off. And the exception was an instrument run by Michel Doherty, who just a month or so ago was appointed as our astronomer royal, but is a professor at Imperial College down the hill. And Michelle and her team studying the magnetic fields of planets. They had an instrument called a magnetometer strung out on a boom away from the spacecraft. And they were interested in how Saturn's magnetic field interacted with Titan and the other bodies in the system. They decided they wanted a dress rehearsal for when they encountered the things they actually wanted to study. And they thought that this inert ball of ice would be perfect for such a rehearsal. They thought that as Cassini flew past, they would record data, they'd check their data, and they'd expect to see absolutely no change at all. There's no way that Enceladus should interfere with the planet's magnetic field. They carried out this plan, they got their data, they did the cursory checks that one might normally do if one is rehearsing. They checked they had the right amount of data, they looked and checked that the voltages recorded by the instrument were what one expected. And then they did something quite unexpected, which is that they decided they should do a proper dress rehearsal. They decided if they were going to be serious scientists, they should treat all their data equally, and they did all the work that you do on data where you were expecting a result. They spent time calibrating it, they spent time checking the instrument performance and doing all the checks that one would do. It's months of work. And at the end of that process, they realized that as Cassini had flown past this small moon, there was a change in the magnetic field, quite a dramatic one, that no one was expecting. They didn't quite believe it themselves. They went back to data from the previous missions, the Voyagers in the 80s, where no one had ever looked at the data as Voyager flew past Enceladus. So they found a similar hint that this small moon was interfering with the magnetic field of the planet. Michelle flew to California, went to JPL, where as the only woman leading a mission and leading an instrument and the only European, she persuaded her colleagues that next time the spacecraft flew past Enceladus, they should turn the cameras on. And in fact, they should go closer than expected. They flew just a few hundred meters above the south pole of the moon and took this spectacular picture. Because what's happening on Enceladus is that there is water shooting out of the moon into space. These are now known as the fountains of Enceladus. The probe flew straight through them, giving itself the only interplanetary car wash that we know of. And this is spectacular because it tells us that this moon, which is made of water ice, has an ocean underneath that ice, locked away from the rest of the solar system. And what's more, because they flew through this water, we could tell things about it. So they know, for example, that it's salty. And that means that there's not just an ocean, but there's an ocean floor down there as well, a place where water and rock are interacting with each other. And so that begins to sound a bit like the kind of places in the early Earth where we think that life got going. We also know that this water's slightly fizzy. And I know it sounds like I'm selling you on an exotic brand of mineral water right now, and I wish I could sell you a glass of Enceladian water, but the fact that it's fizzy tells us there's chemistry going on, that there's activity there. And so this is a place in the universe, in the solar system, that we didn't know about, where we have energy, chemistry, and a location like that where we think life got started. So Enceladus went from being a boring lump of ice to our top astrobiological target. This is the place where, if I had to bet, we will one day find life in the solar system when we go back there. But it was discovered by accident. And actually, we've learned that this kind of world, with an icy crust and an ocean underneath is very common. This is Jupiter's moon Europa. Several of the big moons of Jupiter seem to have this sort of geography, I suppose, with an icy crust and a hidden ocean. Two probes, JUICE, a European probe, and Europa Clipper, an American one, are on their way to Europa right now to investigate this and answer a crucial question, which is how deep the ocean is underneath the surface. For Enceladus, you can just sample the water by flying past. For Europa and the other moons of Jupiter, we may have to dig one day, but we need to know more about the size and extent of the ocean. And we'll know that in the next few years, thanks to these missions. Even Pluto, which is definitely not a planet, and we can discuss that later, but Pluto, which is a waterized world, seems to have this sort of ocean, or at least slush, underneath the surface. So these worlds are much more dynamic than we thought. And when we look out at the solar system, when we look out at the galaxy, and we look up at the night sky, this is just a gratuitous picture of the night sky at this point, but when you look up at the night sky and we realize and start to think about all the worlds that we now know are out there, maybe when we think about habitats for life, we shouldn't think about rocky worlds like the Earth. Maybe the most common habitat for life in the cosmos are these icy oceans locked away from the rest of the solar system. I really like to imagine, in the Enceladus Scientific and Literary Society institution, maybe there's a dolphin somewhere explaining that life is technically plausible on the surface of a rocky world like the Earth, but exposed to sunlight and cosmic rays and solar flares, it's very unlikely that advanced life would survive in such conditions. I do talk in the book about the search for life because, of course, that's the ultimate surprise. And in particular, I talk about how that's entwined with the history of radio astronomy, which gets started in the 1930s, mostly by accident, by a bunch of people who were trying to understand interference with long-range radio communications. But also because radio astronomers have had a habit over the years of stumbling over all sorts of unexpected phenomena in the sky. The example that's known to lots of people is Jocelyn Bell Burnell's discovery of pulsars, spinning neutron stars, the remnants of long-dead stars that beat out a signal many tens of times a second back when she was a graduate student in Cambridge. A story told, incidentally, on A Recent Sky at Night, which is available on the BBC iPlayer, so I don't need to tell that this evening. But I thought I'd tell you a story about this place. This is the Parkes Radio Telescope in Australia. This is affectionately known as the Dish. It's most well known for being the antenna that brought back the video pictures from the Apollo 11 landing and the one small step onto the lunar surface. And there's a whole other story that's told elsewhere about the desperate scramble of astronomers to make that work for NASA. But in my field, Parkes is best known for looking at the changing radio sky, for looking at things that explode or change at these wavelengths. And about 20 years ago, a group of astronomers were looking through the archival data from this telescope, and they found a hint in the data of a burst of radio waves that seemed to be coming from the distant cosmos. Inspired by this, they did a systematic search, and they found indeed that they were receiving these bursts of radio waves that they called peritons from all over the sky. And that's really important because if these things had been associated with the solar system, then they would have followed the zodiac in the sky. They would have followed the path of the planets, the plane of our solar system. If they'd been associated with the galaxy, then they'd have followed the Milky Way. But because they were all over the sky, they must be associated with the distant cosmos. So these must be very powerful bursts of radio waves. It's a very exciting result. There must be some exotic process out there in the cosmos that's creating these bursts of radio waves. And astronomers like talking about explosions. So people got quite excited about these things. And other telescopes around the world started to try and follow up on this exciting discovery. But no one else could see these things. Jodrell tried, the Americans tried. No one else could could pick up these peritons. And the astronomers in Australia were confident that their equipment that they'd recently upgraded was more sensitive, their techniques more robust, their machine learning better than anyone else. And so for a couple of years, they believed that these things were real. They got a certain amount of publicity for being able to detect these distant explosions. At which point they got an email from a retired microwave engineer who asked a question that no one had thought to ask, which was, what time of day do these things happen? And so they made the plot, and here's the time of day and the number of peritons. And as you can see, these explosions from the distant cosmos seem to know when it's lunchtime in eastern Australia. And what had happened was this guy had recognized the type of signal that they were seeing. And it turned out that the microwave oven in the visitors center was malfunctioning in such a way that if you're ever impatient and you open the door of your microwave before it goes ping, it should shut off instantly. This one wasn't. So every time anyone was impatient for lunch, they emitted a burst of radio waves, which could be detected by the dish. And of course, it would be detected wherever on the sky it was pointing. And so this thing, these things turn out not to be distant explosions, but rather delayed lunches for school children in the visitor centre. It's a great story. I really like it. It's a nice tale of scientific hubris, but there's a kicker that's important. Astronomers elsewhere were frustrated by their inability to see what the Parkes radio telescope had been seeing. And so people had improved their techniques for finding bursts of radio waves. And a few years after the Periton debacle, an astronomer called Duncan Lorimer was looking through data from the same telescope and found a distant burst of radio waves. This one was real. They could be detected by other observatories. We call them, because astronomers are bad at naming things, fast radio bursts, because they're bursts of radio waves that appear rapidly in the sky. And this is the CHIME telescope in Canada, built for a completely different purpose, which has now detected about 6,000 of them. I'm not sure whether I'm allowed to tell you that. The paper's not out yet, so please just forget. They've detected lots. Let's go with lots. I forget which bits are public and which aren't. Anyway, these things are real. They're strange objects. They happen at different frequencies. They're usually in the distant universe, but we've seen one in our own galaxy. Some of them repeat, and others don't. And when they repeat, sometimes they're at the same frequency and sometimes they're not. And I was going to say that we have no idea what these things are. That's not quite true. I went through the literature just last week, and there are 52 good ideas as to what these things are. And presumably only one or two of those ideas are right. But we only knew to look for them because we were chasing down a broken microwave in Australia. Even mistakes can inspire accidental discoveries, can inspire you to look for things that you didn't know you were looking for. At this point, I should probably tell you about my own adventures with the unexpected. One of the great triumphs of modern astronomy is that when we do look at a sky like this, we now know something that we didn't know 10 years ago, which is that almost all the stars in this picture, almost all the stars you see when you go outside and look up on a clear night, almost all the stars in the galaxy have planets going around them, are hosts to solar systems. And there's a certain kind of theoretical mind that refuses to be surprised by that. After all, the physics and the chemistry that constructed our solar system must be operating throughout the galaxy. So what happened here, it makes sense, would happen elsewhere. But we could have been winners of a cosmic lottery. We may have been the result of, our solar system may have been the result of some unspeakably unlikely process. And it turns out not. Planets are common. Actually, planets like the Earth are also common. But this has sort of changed how I view the night sky. I now see it as a sort of map to worlds that we can explore. And I can even show you some of these planets. So this is an image of a star called HR 8799, taken with the Very Large Telescope in Chile. I told you we were bad at naming things. We're actually building the extremely large telescope at the minute, which will come on stream shortly. And we were going to build OWL, the overwhelmingly large telescope, but we can't afford overwhelming. But we can do extreming. So this is a star, or rather, this is the opposite of that. This is using an instrument called a coronagraph that's tried to block out as much light from the star as possible. So the yellow thing in the middle is not what stars look like, that's a placeholder. The gap there is where the star's light would be. But these blobs around the outside, if we look at the star over several months, and in fact several years, what you can see is there are 4 blobs on this image that rotate around the star. And these are real planets moving in orbit around a distant, well, a relatively nearby star. It's 130 light years away in the constellation of Pegasus. But what I like about this is an animation that you've seen 1,000 times. On every Brian Cox program, on many Sky at Nights, you always see planets moving around the star. Well, this is the real thing. And we've got to the point that we can do that with real data. But for most of the planetary systems that we've detected, I can't do that. Not because the planets are too faint, but because the stars are too bright. Their glare blocks out the planet. And so what we have to do is we have to find indirect means of discovery. So this is the sun. You'll remember that from a month or so ago. And this is a video from a day in 2012 taken from a beach in Queensland where Venus travelled in front of the sun. These are called transits. They happen in pairs a couple of years apart. The next one's in the early 22nd century. But on the left is the video, and on the right is just the output from a little photometer. It's something that measures light that we nicked from the university lab. And what you can see is one of these incredibly simple astronomical results. When Venus is in front of the sun appears a bit fainter. Yeah, that's about as sophisticated as the physics of this measurement gets. When there's something in the way of the star, it appears fainter. But if you can monitor a large number of stars, if you could do that with a precision that would take your breath away, down to a fraction of a percent of brightness, and you get lucky such that any planets around those stars happen to orbit in the plane that we're looking at, then what happens is that you can deduce that there are planets there because you see a repeated pattern of dips every time the planet gets in front of the star. And you can even work out how big the planet is because you can look at how long it takes for the dip to go from top to bottom. That gives you a sense of size, and you can tell how long the planet's year is, how long it takes to go round its star, because you can time the distance between dips. And so this is the game that we play. We particularly do this from space. There are satellites called Kepler and then TESS, which NASA launched, that look at large numbers of stars at once, hundreds of thousands of them, and monitor for these dips. We're launching a European version called Plato, which will look particularly for Earth-like and Earth-sized planets. Plato launches in, I think, about 2027. Oh, it might be next year. In fact, it is next year. And we took all the data from TESS and from Kepler, and through my work with a citizen science platform called Zooniverse, we put it online on a website called Planet Hunters, and we asked people to help us sort through the data. And the nice thing about this is that people are willing to help, but also they're willing to find the unexpected and unusual. So this is the most exciting graph I will show you this evening. I'm going to reveal it in stages to increase the suspense, though I can feel you're already excited. Now there's a graph on the screen. This is the brightness of a star called KIC 8462852, for those taking minutes. And just after this Kepler spacecraft started to observe it, there was a dip in brightness. This was spotted by our Planet Hunters volunteers. This could be a planet. It's quite a large planet. It's nearly 1% of its brightness has gone. So this could be something like a close-in Jupiter. But one dip isn't enough. But there is a second dip, so that's pleasing. This is about a couple of months later. But there's no third dip. And so whatever's causing this, it's not a planet. Planets don't go around once, twice, and then go on holiday or change their orbits or something. So maybe this is a giant star spot or some problem with the camera or something that had happened in the star's system. No one paid really much attention. This sort of thing happens all the time until a year later where this happened. The star faded by about 20% over the course of a day or so, and then it came back up to full brightness and carried on as if nothing happened. And stars don't do this. None of the other 200,000 stars none of the other 199,999 stars that we studied with this telescope ever did anything like this. And so the volunteers noticed this, and they were really paying attention a year and a half later when this happened. It was like somebody had got hold of a dimmer switch and played with it for a month. The star faded and brightened and faded and brightened and dipped all the way down to 30% of its previous brightness and then came all the way back up. This doesn't make any sense at all. And so the volunteers alerted us of this. We spent a long time trying to work out if this was real. We looked at the star with new telescopes, didn't seem to be doing anything unusual. We looked at neighbouring stars in the field that didn't seem to be doing anything unusual. We got as far as, there was an awful week in which we spent an awful lot of time trying to work out which pixel of the camera this star landed on every time we took an image of it, in case there was some systematic effect in the camera, but we couldn't find anything. And so eventually we gave up, and we wrote a paper, which we sent to the journal, that basically said, this is led by my colleague Tabby Burragin, we sent in a paper that said, look, we found a weird star. And we got two pieces of feedback from the editor. The first one was that the paper was unacceptable unless we had an explanation for what this was. I'll come back to that in a second. The other one was more problematic initially, which was that the volunteers had called this the WTF star. So we called it the WTF star. And the editor, slightly sheepishly, pointed out that all acronyms have to be spelt out in full in the pages of the monthly notices of the Royal Astronomical Society. So WTF stands for Where's the Flux, which is, of course, the scientific problem here. And we also needed to come up with lots of these people are volunteers, by the way. They were people who helped us identify the star in the first place. We had to come up with a theory, and what we came up with was we decided we were going to blame comets. So comets are mercurial creatures. They're icy snowballs, dirty ice balls, but they sometimes break up. This is a 19th century illustration of a comet called Comet Biela, which came around every 8 years in the early 19th century until February 1846, where it was seen in two pieces. Then it didn't turn up for its next rendezvous, and then we got a really good meteor shower 8 years after that. And so this is a comet that disintegrated. So we said, okay, what's happened around this star is that there was a comet, it split into bits, into cometlets, in fact. Here's an unconvincing artist's impression of that. And then we can arrange these comet bits to block out the light from the star and explain the pattern that we'd seen. I don't know whether that's convincing or not. I think it has the problem that I can explain any pattern I like just by moving different bits of comet around. But it seemed plausible to us, and it got the paper published, at which point we heard from everyone in the world who's ever studied comets, who point out that this thing would have to be about 10,000 times larger than the largest comet we know of in our solar system, and it would have had to break up just a few months before we happened to start looking at the star, and that would have to be a rare event, because otherwise we'd see lots of these things. So we gave up on the comet idea, and other astronomers started to publish their own ideas about what this star was. One of them, which got a lot of attention, was this paper. This is the GHAT Search for Extraterrestrial Civilizations with Large Energy Supplies, paper 4. We'll be taking papers 1 to 3 as read this evening. The signatures and information content of transiting megastructures. I found out about this paper when the phone rang in my office on a Monday morning, and it was the Daily Mail saying, "I hear you found aliens." I'm not great on a Monday morning, certainly not before coffee, and I genuinely just said, I don't know, I'll check and get back to you, and put the phone down, and then opened my email and found this paper. And the idea here is that if you're a civilization worth your salt, you're getting your energy from solar, or I guess stellar power. And the easy way to do that is to surround your star with a fleet of orbiting solar panels. An idea that's sometimes called a Dyson sphere or a Dyson swarm. It actually goes back to the brilliant 1930s science fiction author Olaf Stapledon. So you have this fleet of orbiting solar panels, and if the solar panels are blocking out light from the star, well, you might see dips in brightness as they pass in front of it. Is that convincing? It has the problem that the comet idea had, in that you can explain any pattern, but perhaps it's worth considering. And we ended up using a fleet of robotic telescopes around the world to try and disprove this hypothesis. Telescopes like this one in Hawaii. And what we found was that When a few years later, we eventually found the dip happening again, we caught the star at the point where it was dipping. We found that if you looked with a camera that was sensitive to blue light, you saw it dip in brightness, but not as much as if you used a camera that was sensitive to red light. And what that tells you is whatever's blocking the light isn't solid. It must be something more like a dust cloud or something like that. So no alien solar panels, but we're still arguing about this star. And like the case of the malfunctioning microwave, this has actually inspired a whole host of astronomers to look at a whole host of other objects. This is a recently discovered star. This is a month's worth of data. This is a star called HD 139139, where it has 37 seemingly random dips in brightness over the course of a month. And the reason I like to bring this one up is that A, it was found by people inspired by the WTF star, but also Andrew Vandenberg, who led this project, was asked by a journalist, he said, well, could this one be aliens? And Andrew said, well, in astronomy, we have a long history of not understanding something, thinking it's aliens, and then later we find out it's something else. So this is probably another one of those. And I think that's a lovely description of how the scientific process actually works. In the 5 or 6 minutes I've got remaining, I think I want to return us to the outer edges of the universe. I want to talk to you about a result from the Hubble Space Telescope, because I think this is still the iconic telescope, a project that was first dreamt of in the 1940s, that launched in about, I think it was 1989, somewhere around there. The dream of a generation to put a telescope in space above the Earth's atmosphere to stop the stars twinkling and give us a crisp, perfect view of the night sky. And therefore, rather distressing when the first images came back. Here's one of the first images on the right, and on the left is a ground-based image from Chile, the same patch of sky with a telescope of about the same size. You can see that these two images are pretty much the same as each other. You can just about see the one on the right at the top. That's a double star. You can see it's a bit crisper, but this is not sort of $10 billion worth of improvement. What had happened was that the machine that was testing the Hubble Space Telescope mirror, which had been engineered to a precision such that if you blew it up to the size of France, the largest bump on it would be about that size, a couple of centimeters at most. The testing machine had an error in it. In fact, it had a washer that was left that shouldn't be there. And so it precisely guided the engineers to make the telescope exactly the wrong shape, like a malformed set of glasses. And so this was a political disaster, an astronomical disaster as well. There was no funding to replace the telescope, but engineers were able to devise essentially a set of corrective optics, this thing on the left called COSPAR, and astronauts from the space shuttle were able to go and capture the telescope and install these corrective optics. And so a few years after launch, we went from blurry images of the universe like this to beautiful images like the one on the right. That was about 1993, and for 2 years after that, everyone involved in the project worked incredibly hard, round the clock, to get back the data that they'd lost from those first few years, to win back, really, NASA's reputation and prove that this thing was a success. It was a time where they were measuring their success in the number of New York Times front pages that Hubble images were sitting on, because you've got to speak to your constituents, the politicians, if you're going to build expensive space telescopes. By the end of 1995, everyone involved in this project was on their last legs. People desperately needed a break, preferably over the holidays, over Christmas. And the problem that the center director, Robert Wilson, had was that it wasn't politically acceptable to shut the telescope down for a few weeks so that people could have some time off. They were still in this mode of trying to prove that they were productive and useful. And so he resurrected an idea that had been rejected by astronomers for Hubble. He wanted to make the simplest possible observation. So what he decided to do was to take the night sky, take actually quite a familiar bit of the night sky. In fact, you can just see there's the plough there. Take this patch of the night sky right here, in which there appears to be absolutely nothing. No stars in our galaxy, very little dust, no nearby galaxies, a patch that appears to have absolutely nothing in it, and then point the telescope towards it for 100 hours and collect whatever light it receives in a hope of seeing the faintest objects ever discovered. Now, the reason that this idea had been rejected was that astronomers are capable of doing calculations, and people had worked out that if you took the galaxies that you see around us today, you put them in the early universe, you allow their light to travel towards us for billions of years, and you work out how bright they'd appear, you find that they're too faint to be detected, even in 100 hours of observation with the Hubble Space Telescope. And so the almost universal expectation was that such an image would be blank. They did it anyway, and in January 1996, they released to the world one of the iconic images of the space age. This is the Hubble Deep Field. There are, in this tiny patch of sky, 4 stars, and every other dot you can see is a galaxy. Some of them with light that's been traveling towards us for 10 billion years. So we're seeing the first few billion years of the universe's history. And the mistake that had been made is that the early universe is not like our local universe. The galaxies that exist there started their lives, it seems, in a burst of star formation. It's like a firework display. The universe got going after the Big Bang with a bang, and we see this violent and exciting epoch revealed in the deep field. And this mode of imaging, where you just stare at one patch of sky, has become a standard thing that one does with telescopes. In fact, we're about to do it with our newest toy. I want to end by telling you about the Vera Rubin Observatory, this thing, which sits on a mountaintop in the Atacama Desert in Chile. This is a 20-year-old project that in the next few weeks will start routine operations. It's as big as the biggest telescopes in the world today. It has an 8.5-meter mirror at its heart. The mirror sits down in this cell. This is before we installed it. And it can swing across the sky. But its real secret sauce is that, as well as a field of view that covers an area 40 times the size of the full moon, this thing has the biggest camera ever built. This is a 3,200 megapixel camera, which is going to be exposed to the sky. And to give you some idea of what we're going to see, here's a deep field from Sloan, from that survey that we flew through near the beginning of the talk. You see galaxies, few stars. I'm going to show you a 3-hour exposure with this new telescope and camera that was only released a month or so ago. Bear in mind, we're going to have 10 years worth of data from this survey in the end, but here's 3 hours with our new telescope. And the difference is stark. We're getting to the point where almost every point on this image has light in it. We can see distant galaxies, we can see faint galaxies. The nearby galaxies have these beautiful halos of light that come from stars that are being kicked out. And this telescope, which will produce 30 terabytes of data a night sent around the world, is about to revolutionize astronomy. But it's only designed to do this because people needed a couple of weeks off over Christmas in 1995. I hope that's been fun. I hope that when you see Rubin images, which you will in the newspapers in the next few years, you'll realize that it's not all the result of great planning and careful work. Sometimes we stumble over truth. And I hope you'll think about our accidental universe. Thank you very much.
Thank you very much, Chris. That was absolutely fantastic. It's given me all sorts of new insights into astronomy, things I didn't know. That's wonderful. Now, I'm sure we have some questions for Chris. Yes, gentleman here. Oh, sorry. Yes, yes.
What is interesting about the Pleiades? I've heard that spoken of several times. What is interesting about the Pleiades?
Yeah, many things. So this is a cluster in Taurus that, for starters, they're easy to see. So they're a nearby young cluster of stars, and so they're an opportunity to study stars that have just formed. They're a few million years old. And one of the things we're interested in is how quickly they scatter to the galactic winds. How long do stars remain in their birth cluster? So if I showed you the Orion Nebula at the start, we can see there's a cluster of stars deep in the middle here called the trapezium. So in a few million years, this gas will have blown away. You'll be left with the stars, but they will slowly disperse. And so the Pleiades helps us understand that process. Another thing that's interesting about them is that they're a yardstick in our distance ladder. So if we can understand the distance of the Pleiades, then we can begin to use that measurement to understand the distance to other things in the galaxy and build up our ladder. So there's a lot of argument about exactly how close they are. There's a satellite called Gaia that's been mapping the nearest billion stars, and the Pleiades are an anchor in that.
How many light years?
They're about 200, but my colleagues would want me to give you a precise answer, and I don't have the number in my head. But about 200 was the most accurate we had until about 2 years ago. But yeah, no, they're an interesting cluster. Thank you. Also good through my small telescope. Great in binoculars.
Gentlemen, there may be Bill, you could give him the microphone. Do you just hang on for the microphone?
Microphone coming towards you.
So they can hear you at home.
With the assistance of the audience.
AI has been transforming a lot of fields recently. What impact has it had on your field?
Yeah, a lot of my own work is with machine learning. Because we've got this data set coming, we've got our 30 terabytes a night or worse. We built a system for the Rubin Observatory that tells us whenever anything changes or moves in the sky, and we're a month from getting about 20 million messages a night. I think so obviously a lot of machine learning can help with that, but I think one of the things that I'm interested in is that if you're trying to find the unexpected, we're finding that machine learning can do a good job of finding can tell you how unusual something is, but most unusual things are boring. The camera broke, there was a bright star, there's a satellite that got in the way. And so the hard bit is to get the AI to tell you what's interesting. So we see a place for human-guided machine learning where the machines tell you what's unusual and the humans tell you what's interesting. So we're trying to build that sort of hybrid system. There's all sorts of stories about scientific AI that we're different from, say, Google. If you ask a question of Google that's 1 in a million, Google probably doesn't care whether it gets that right or not, as long as it gets the bulk of queries right. For us, the object that's 1 in a million is probably how you test your theory. And so we have to build our own different systems that care about such things. But you're right that it's exciting technology.
Whose hand up was first? I think, yeah.
Recently, there's been news about a potential biosignature found on Mars by the Perseverance rover. What's your personal take on that?
Yeah, so Perseverance rover is a chemical laboratory that's driving around Mars, armed with a laser to sample rocks. Its main job is to pick up samples that we hope one day another probe will go and get and bring back to Earth. And they found a rock that has evidence that it's interacted with water in the distant past, about 3.5 billion years ago, but also has in the rock the kind of mineral signatures that if you saw them on Earth and you were a first-year undergraduate geologist, you'd go, this is the result of bacterial activity. If that rock was on Earth, we'd absolutely believe that bacteria had altered it. Is that what happened on Mars? I think we're not sure yet, partly because it had 3.5 billion years to happen. So all sorts of things that might be unlikely could happen in that time. So there's a lot more work to be done to work out if that really is solid evidence of life. Mostly, everyone I know who says this stuff wants to get that rock and bring it back to the lab here, where we can use tools that you can never put on a Mars rover. And so what we're hoping is that the rover has sampled that rock and others like it. We're hoping that in the next 10 years, there'll be a set of missions to go and get those samples and bring them back, and then we'll have a good chance of answering the question. So probably by the time you're working on this stuff, looking at you, we'll have a sample for you to put in the lab, and you can answer your own question.
Okay, there's someone over there. We'll come to gentleman here.
You said you might like a nudge to talk about Pluto.
Oh, yes. Yes. Well, I can advertise. So I have the great privilege of being Professor of Astronomy at Gresham. And I get to talk to an audience down at Conway Hall and online. And I learned early on that they really like Pluto, and they're vaguely upset that it's no longer a planet. So I have a lecture coming up in, I think, May about why Pluto's not a planet anymore. But I think actually the more interesting thing is that this is an image from a probe called New Horizons that flew past it. And it's a much more varied and spectacular world than anyone expected. In particular, there's this feature here, which is sort of heart-shaped. You can see half of it on here, called Sputnik Planeta now. And this is an icy surface, and it seems to refresh itself every few million years. So there must be some activity underneath. Up here, there are mountains made of water ice. And this dark material appears to be deposited by interactions with its moon. So this thing was a point of light until, it's actually just gone 10 years since this flyby happened. And so we spent 80 years trying to understand Pluto as a point of light. And now we get a set of pictures and we get all these other questions about it. So I think one of the things that Pluto does is it tells us we should go and take a close look at all of these things. And it's a fascinating and interesting world, whether or not it's a planet or not. But thank you for prodding me.
Gentleman here.
Thank you very much. It's a fascinating talk. If I've understood you correctly, as you produce more and more accurate and perceptive cameras and telescopes, so you're looking deeper and deeper and further into the universe, and therefore further and further back in time. I suppose the question I'd be interested to know is, as an astronomer, is there a hypothesis that you're going to find an edge to the universe?
It's a good question. So I'm going to fall back on my status as an observer. And so there's definitely an edge to the observable universe. So probably some of the small red dots in this image are from galaxies whose light has been traveling towards us for 13 billion years. They must be close to the first generation because we have good evidence the universe is 13.8 billion years old. So we have this region of the universe that we can see, and that has an edge. The edge is marked by something called the cosmic microwave background, which is light that was emitted 400,000 years after the Big Bang. So that's our limit as to how far back we can see. Whether that's a real edge to the universe, I don't know. We think that our observable universe is only a tiny fraction of the whole. So if there is an edge to a universe that could well also be infinite, we would find it very hard to discover that from our tiny perspective. It would be like trying to work out the geometry of the Earth based only on measurements I can make on this stage. It may be possible, but it would be very difficult. Thank you for the question.
Okay. Right. Well, thank you very much indeed, Chris. Thank you, the Hines family, for sponsoring tonight's lecture. As you know, we always have some wine after our lectures. You will notice when you come next door, the quality of the wine is rather better than you may be used to here, and the quality that we have food as well. So please do come and join us. Chris, we have copies of Chris's excellent book, Our Accidental Universe, which he will be happy to sign for you. I can tell you it's an extremely good read. I strongly recommend it. Let us say thank you again to Professor Chris Lintott.
Thank you. Great.
Brilliant.
Yes, it's good. Excellent. That's 1 minute over. So,
Good man. Yes. Good man. Well, what did we do? We started 5 minutes ago.
Yeah, exactly.
Excellent.
Great, good.
Lisa.
Well,